So now that you've got the bird's eye view of what we're doing, let me go ahead and start showing you the functional programming code that performs this parallel searching, and we'll focus on how to start and join threads using functional programming features in Java. And so I'll demonstrate how to program things to have essentially a thread per input model, where you can see that for each input file we have, for each work of Shakespeare, we're going to have a separate thread that will do all the searching on that particular work of Shakespeare. And by searching here, we're looking for the list of phrases that match against that particular input. Okay, so if you take a look at the run method, this is the run method on that search one-shot thread join test class. The run method is going to go ahead and start a group of threads that will search for the phrases in parallel. And this is illustrating the functional programming features here in a second. So, if you have the work of Hamlet, we'll search for the phrases in that one thread for Hamlet. If we have Macbeth, we'll search for the list of phrases in Macbeth in a separate thread. And of course, each of these threads will be mapped to a processor core. The run hook method is actually an object-oriented concept because this thing inherits, the run hook method is a method that can be overridden and customized, and you'll see a couple of cases where we do that. Just for a recap, and this is probably a good question to think of for the quiz, what is a Java thread? A thread is a unit of computation that runs in the context of a process. So thread equals unit of computation to process a stream of instructions. A process, in contrast, is a unit of protection and management, resource allocation. So the process is sort of the box in which multiple threads run. And you can sort of see that here visually. So the little gray round angle, as it's called, kind of like rectangle, but it's rounded edges. So the round angle, that's a process. And within this process, we have multiple threads. And I can pretty much guarantee that that will be a quiz question. Yes? Oh, great question. So the question here is, can thread maintain state? Let me answer that question first by saying, one of the things that a process does is it's a holder, it's a box, it's a container, although I have to be careful how I use that word because it's been hijacked by a whole other paradigm of modular program composition and packaging called containers. But a process is a box that holds, a logical box, that holds a bunch of state. It obviously holds the state for things like all the static variables and all the heap that you think about. If you have a Java program, you say new, that comes from the heap. So a process maintains all of that stuff. A process also contains, of course, the state for the threads, to be able to allocate those threads in virtual memory and let them run, and the thread objects themselves. So clearly, a process has a bunch of state, but then each thread can also hold state as well. And does anybody here who's taken the operating system course in particular, does anybody remember what kinds of state can be stored in a thread? What would be examples of things that might exist in a thread? Yes, sir. Great points. Yes, so let me rephrase that for the recording, if nothing else. So within a thread itself contains a bunch of state. Let me see if I have a picture here that illustrates this. There we go. So if we look at this picture here, so the gray round angle is the process, and then within the process will be a bunch of threads. And the stack that you're referring to is the funny thing here that's the kind of, the stack of colored blocks, if you will. So each of these little blocks corresponds to what's known as an activation record. And an activation record just keeps track of the state for a given method call, and that would include typically things like its local variables. If you have a method in Java that defines a local array, or a reference to some object, or a primitive instance like int or care or whatnot. In that particular case, the state for those things would be stored on the activation record. And as you make a bunch of method calls, you of course will build up a stack of activation records, and then as they return, the stack will pop, 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 and as you make the method calls, the stack will push, 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 push. So that's one example of something that could be stored that's state-oriented. There's obviously other state that's stored as part of a thread as well. There's things like the instruction pointer that keeps track of where you are in the stream of instructions, for example, the bytecode instructions. There's also things having to do with registers. There's something called thread-specific storage. So there's a bunch of things that will be allocated in the context of the thread itself. But also to the point we were just discussing, the bulk of the actual objects state, the fields, the contents of the fields of objects, those typically live off in memory allocated from the heap, which is then accessed by various references that are either stored in the activation record as local variables in the runtime stack of a thread, or could be stored as fields in objects that also live in the heap. So that's a very quick synopsis of memory management. But yes, threads can store state, processes can store state. The bulk of the state is typically, in Java programs, is typically allocated out of the heap. But it's accessed and managed in the context of threads. Okay, so that's what a thread is. So what we're going to do here is we're going to have the run method. This is the run method that's kind of the entry point into the whole program. It's going to go ahead and make a call to a factory method. Hopefully people here remember what a factory method is from the 251 course. A factory method is just a method that makes something. So it creates something, and it shields the caller from the details of how it made those particular things. So in this case, the factory method is called make worker threads, and it's going to give us back a list of worker threads. No surprise, and we'll look at make worker threads in a second. The way we're going to make these worker threads is we're going to pass a method reference, which will be passed to a method that expects, we're going to pass a method reference to a method, make worker threads, that expects a functional interface, or it has a parameter defined to be a functional interface. In this case, it'll be the functional interface, as you can see here. And so process input is a method, and we pass a reference to process input to make worker threads. And if you take a look at make worker threads, which is what we're calling here, it's expecting a functional interface. And what this buys us, why are we doing all this stuff? What this allows us to do is it allows us to be able to reuse this make worker threads factory method, but change what tasks the threads this method creates by simply passing in a different parameter, which is a function. And this particular function maps strings to void, and you'll see why it does that in a second. All right, so the first key point to recognize here is that we're using functional interface function in order to be able to parameterize what we pass in as the argument to the make worker threads factory method. And the whole point of that is just to be able to parameterize. Remember we talked before about how Java 8 makes it easy to do functional parameterization or behavioral parameterization. We can pass in different behaviors and get different results. So the make worker threads method can be reused in many different contexts. So speaking of which, let's take a look at make worker threads. So here's make worker threads. It's the factory method that creates a list of threads that will be joined by the main thread when all the processing is done. So here's how it does this. It goes ahead and it makes a new array list, which is empty. So we have an empty list of threads. And then for each of the input strings in the inputs, remember the input here is the works of Shakespeare. So for every work of Shakespeare, for each work of Shakespeare, we're going to go ahead and create a new thread, and that thread is going to be given a task to run as a lambda expression. So you can see this is a lambda expression. Remember how we talked before about lambda expressions and how they can be used as a shorthand to give work to a thread or whatever, but in this case it's a thread. So we make a new thread that has a lambda expression, which is task, because remember task was the function parameter passed in, and remember function has one method called apply, so we say task.apply to input, where input is the shorthand name for the work of Shakespeare. Remember, if you go back here, for each string in the complete works of Shakespeare list, where input is the name of that string, this is using Java type inference or type deduction to figure out that this is really a string, because it's a list of strings, so this is a given string. So for each string in the list of strings, we go ahead and we're going to create a lambda expression that will apply the task to that input string. Now keep in mind that when we make this lambda expression call here, there is no work being done. All this is doing is saying when the thread is started, this is the computation we want it to perform. So this is actually not doing any work at this point. It's making a thread that has work that will be done when the thread starts to run. And then we go ahead and we add each new thread to our worker threads list. So when we're all done, we've iterated through all the works of Shakespeare. We've made a bunch of threads. They've not been started yet, but we've made all the threads. And each thread will apply a task on the input. And then the last thing we do on the way out is we say, return this list of worker threads. So now what we've done, I mean, at a very high level, what we've done is we've bound the task that we passed in as the parameter. We bound each task to a thread that, when started, will perform some computation designated by the task on each input string in parallel, in an embarrassingly non-dependency-centric way. Okay, so now when we call start on each thread we just created, then each of these worker threads will be given its own runtime stack with the stack of activation records we talked about, making a call stack, along with all the state that's associated with that. And then each of these threads can start to run in parallel, and they can do their thing. All right, so that's kind of the big picture. I'm sort of visualizing what I'm about to talk about. And then here's how we do this. We get back our worker threads list from make worker threads factory method, and then we say worker threads for each, so for each of the threads in the worker threads list, and then we say thread : start. So we pass in a method reference for each of these. We pass a method reference in, and this method reference comes from the Java threads library, and what that'll do is it'll start each of the threads in the list of worker threads. And we'll talk, when we do the evaluation part, we'll talk about why this is a win, but the key point to come away with is we never have to worry about fence post errors, we never have any off by one problems, because for each thread in this list, we're going to start the thread. So I think you'll agree with me that this is very declarative. We're saying what we want to have done, not so much how to do it. I'll show you some examples of the how to do it thing that are going to get you into trouble if you're not careful, because it requires great attention to detail, and we get tired sometimes and don't have enough attention to detail. So what's happening here is there's a thread created for every work of Shakespeare. So this is an example of a thread per work, work being work of Shakespeare, thread per play, if you will, parallelism model, embarrassingly parallelism model. Now, once we've kicked all the threads off, right? So once this has started everything in motion, after all the wheels are in motion, then this main thread, which is the guy calling run here, is going to do something called barrier synchronization to wait for all the other threads to finish. And I'll explain to you in a second why it's important to do this. But for the sake of the discussion right now, here's the way to do it. I'll explain why we do it in a second. This is just the way it's done. So for each thread, we're going to iterate again through the list of threads. And for each thread, we're going to go ahead and join each of the threads. And this is what's called barrier synchronization. And we'll talk about barrier synchronization a lot in next semester's class, but the Cliff Notes version right now is it's a way to coordinate either the beginning of a bunch of threads so they all start at the same time, or it's a way to make sure that all threads end at the same time, or that you don't proceed until all the threads are done. So here's a couple quick examples. There are two different canonical forms of barrier synchronizers: entry barriers and exit barriers. So a classic entry barrier would be something like a starting gate at a race, or if you don't like horse racing, the starting blocks of something like a track and field event where you're going to do the 100-meter dash, and you don't want the person who gets to the starting block first to start running, right? That would be a little unfair. So you wait till everybody's there, and then someone shoots the gun and they all start running. So it's an entry barrier. That's not what we're doing here. We're doing an exit barrier. An exit barrier says we're going to wait at a particular point for everybody else to finish running, and then we'll go do something else. So a good example of an exit barrier might be the person who is responsible for closing down a store when the store is closing, or the store is closed, right? So if you go to Target or Walmart or whatever store you go to, at 9 o'clock the store is closed. Well, at 9 o'clock they don't just start putting poison gas in the store to kill everybody who's in there, right? They say, okay, store is closed, everybody leave, and then someone is responsible for making sure that everybody's left, and then they shut the store down and lock it up and turn off the lights or whatever they do. So at that point, conceivably then that person can leave. So that's what we're doing here. The main thread is kind of waiting for all the other threads to finish, and then when they're all done, it can continue doing something else. Now, why do we need to do this? The reason we need to do this is in Java, if the main thread, well, there's a couple different reasons, but typically what will happen is if the main thread goes away, then depending on various circumstances, that may cause the whole program to shut down. And we don't want that to happen. We don't want the other threads to get killed. We want the other threads to keep running. And that gets us a little bit off track into something called daemon threads versus non-daemon threads, which I don't want to talk about right now. But the long and the short of it is we want this program to have the main thread wait for everybody else to finish, and then it will go ahead and wrap up and print a completed message that illustrates that we're done. No other form of Java synchronization or Java synchronizers is needed or is used in this example. So we don't use atomic variables, we don't use condition objects, we don't use mutexes. We just synchronize on the completion of all the other threads by joining with them. And it's again a bit beyond the scope of this course to talk about this, but one of the things to note here is that the order in which the threads are joined may not be the order in which they actually complete. So if you're searching, very long Shakespeare play, like maybe Hamlet, which is very long, versus some other much shorter Shakespeare play, like Midsummer Night's Dream, maybe, or I don't know, some shorter play, Julius Caesar, it may turn out that the one that's shorter gets done first, but that may not be the order in which the threads were created. So join will simply wait until the current thread that's being joined finishes, even if other threads have already finished. And keep that in the back of your mind, because we'll talk much later in the course about various concepts such as reactive handlers. And sometimes you want the order in which things to be handled to be the order in which they complete, not the order in which you wait for them to complete, which is what's going on here. Okay, so that's a quick summary of how the program works and an illustration of the various functional programming features we've talked about before and how they get applied in the context of this simple example.